Welcome to NX for Manufacturing Tech Tips. Today's tech tip is titled, How to Program Main and Sub-Spindle Transfers on Mill-Turn Machines in NX CAM. Demonstration will last approximately 20 minutes, and we'll stay on the line and open up a chat window for questions and answers. With that, I'll turn the session over to Uwe Edlinger. Welcome, Uwe. Let's get started.
Thanks, Derek. In the next couple of minutes, I want to just show some PowerPoint slides about some challenges, and for each of these challenges, I have then a demo inside NX to show you this some pieces of these challenges. So for the mill-turn programming on a main and on a sub-spindle with probably two machine channels, where each channel is a tool assigned, in this case one top channel and a turret on the lower channel. And I want to talk about these typical requirements for programming of multiple spindle and multiple channels. And in many cases the operation on a mill-turn machine are not as complex free-form surfaces. You may have this, but in most cases you have simple geometry complex in the process, but the geometry itself is in many parts a simple slot or a hole or a pocket. And we provide a functionality in NX to directly program these simple slots, including a simulation of the slot inside the operation. And I want to show you this functionality to how to program slot around a cylinder and how easy this can be done in NX. All of this is for sure part of the NC program simulation inside NX to avoid machine limits and collisions. The next challenge after you program the main spindle, in this case the left side of your spindle with your operations, you have the requirement to move the IPW from the main to the sub spindle. And in NX we have some functionality to make this more or less automatically, and I want to show you how this is programmed in NX. And by doing this with this NX functionality to move, NX CAM functionality to move the IPW from the main to the sub spindle, you can easily move also operation from the main to the sub spindle, and this all is associated to the IPW. So yeah, you don't split the IPW flow. So if you change something on the main spindle, you directly see these changes on the sub spindle. So you always be aware and you always be noticed where the IPW is and where material is to cut. And after this is done, the last function I want to show you is how to implement typically machine cycles, because many of these mill-turn machines do have special cycles which need to be supported. It's more or less not really cutting cycles. It's cycles for steady rest or cycles for like this to have a travel to fixed stop, where the machine tool is moving until it hits the part, and after it hits the part it's doing some machine functions automatically. And inside NX we have a possibility to implement such kind of machine specific functions, not only for the numeric controller, also for all other controller. It's not limited. I want to show this on a numeric controller with this travel to fixed stop functionality, which is not an NX feature. It's a feature from the real machine tool. It's a feature from the controller. But I want to show you how you can implement such kind of functionality inside NX and control this functionality inside NX. The NC output is outputting then the cycle, and so you can easily change the parameters then on the machine tool, because you will see the same parameters on the machine tool as you have seen in NX during the programming. I also want to show you in this example how easy you can implement a special template for this machine tool and to easily program these parts. And with this I change to NX. So you hopefully can see my screen with the machine tool loaded. I zoom a bit out that you can see this. There are already a couple of operation here. On this operation navigator you see that, as for this example, all of this is created with channel 1, so it's only this channel here on the top. On this example I did not use any of the lower channel operation. I will do this with the next example part. I will show you on travel to fixed stop functionality. You will see a dual channel programming. Here for showing you this simple slot, it's fine to have it only on this channel, but it's not limited for sure to only to one channel. You see here a couple of operations which are already created. Hit an F8 and zoom in a bit here. So you see a facing operation here. You see the roughing operation. You see a cleanup here, the area here to create the slot for this pocket. Center drill, and you will see here some pockets. Every time you can show the 3D workpiece how it looks like at this operation. And now, after it comes to an end with all of these drilling operations, there's one feature missing here, which is this slot which goes here on the side around of the part. So how to create this more or less simple slot in NX? For this we have a functionality in NX, and it's called a generic motion operation. I just insert this generic motion operation by inserting an operation and select the generic motion operation out of the list on the possible operation subtypes. The generic motion can be found in the multi-axis dialog. It's here called generic motion. It is in the multi-axis template because it is you can create a 4 or 5 axis toolpath with the generic motion, but from the license point of view it's licensed with the standard 2.5 axis operation. So it is in this multi-axis template, but it's not do not need a 5 axis license. It's done off the out of the box environment. So I select the tool, I select the main MCS, method is not necessarily needed for this. Type in the name, generic motion is fine for this, and I hit OK. And with this it's initializing the generic motion operation type, where I can do directly the simulation here, and I can define my motions here by step motion. So if I go to the select the generic motion and I insert a sub operation, and with this I can define step-by-step motion. For most of the, say 80%, maybe 90% of this slot kind of things, the best possible is the rotary point vector move. All the others are also possible to use, but this is the easiest one and the most intuitive one to use. So I use the rotary point vector move, and with this you will see immediately the system shows the tool here on the MCS 0 position, and at the beginning I position my tool here in the center of this slot, and I select this face here as the alignment face, that my tool is normal to this position. Now I move a bit outside, say 5 millimeters, and I move up, say 15 millimeters for example, to this position. And this should my first position, and I want to move to this position with a rapid movement. And now I just go step by step. I say, okay, that's my first position, that's fine. Now I move back here to -50, go down. hit again, a rapid move, that's fine for this one. I move back this 5 millimeters. I can for sure also select the point again. This should be an engage move. And now I have to go all around to the end here, which is here. Should be a cut movement to this end by this vector. That's my end position. Hit apply, and I retract my tool with a rapid move, say 15 millimeters. And if I hit OK, you will directly see in the list of operation the single sub-operation I create for this tool path. And you will see this 1, 2, 3, 4, 5 movement. This is the first one, and that's the last one. And this means I have exactly 5 points inside my NZ program. And how does it look like now on this machine tool? If I start the simulation, directly inside the operation, you will see that the machine movement is done. It's coming to this point, down, rotate the part, and moves back and home. Now you see another thing which I can fix here quite easily. You see that the Z-axis of the machine tool is still at the position of 180 degree. And for some reason I want to move this back to a 0 degree. And this is also quite easy in this generic motion because I have the option to add machine movements directly here. I can say move the Z-axis to 0, say OK. And now you will see that this operation is coming here. Go to the start point and start the simulation again. And you will see that the last movement is to rotate the Z-axis back to 0. I don't want to make it too fast that we can see it. It's slower because this Z-axis rotating is in rapid motion. So it's quite fast, goes up, rotates back, and the tool is moving home. All of this includes the full collision control, material movement, everything can be showed in this dialog. And if I hit OK, that the generic motion will be as one operation inside my programming structure for this single step motion. That's the first thing I want to show. The next thing I want to show is how to move this IPW from one to another spindle. For this I open a different part. It's already open in the back. No, it's not open, so I have to open it. The back, start up this. This example is more or less the same part, a bit less operation, but you will see here there is a facing on the main spindle. If I go here a bit to the right, you will see the different MCSs, and there are here this is G59 MCS, which is on a sub spindle. So all of these operations are on the main spindle here, and this is the operation on a sub spindle. You will see here the movement on the sub spindle. So how the system knows how the IPW, which is at the end, this one here, move from here to here. The reason why NX finds this out is because of the assembly tree. If I show the two parts, you see that there is a part here at this position, and there is a part here at this position. So you have two parts in the assembly tree. I think last week, 2 weeks back, Gurdip shows the setup, how to set up these two parts in the spindle. And because of this automatically set up, the system understands these two positions of the part, and the blank part is coming directly together with the part. So if the part is moving, the blank part is moving. And these are these two workpieces here inside a geometry structure. This geometry structure with the MCSs and the blank parts and the main zero is coming with the setup template. I think that's also something Gurdip explained 2 weeks back. And if I look to the sub spindle, and if I double click, if I open it, you see the specified blank on the sub spindle, and if I open this, you see that the blank is used from the workspace with an automatic positioning. So this IPW which you see on the right is moved or is at this position because of this automatically part transfer. So how is the simulation now working? I'll just quickly show the simulate with the material removal, and you will see that right now, I'll make this to number 4, the inside the simulation, that the simulation is done. Make it a bit faster. Hopefully you can see it nicely, but it's first cutting the part on the main spindle, and then the IPW is moved to the sub spindle. Right now it's just moved without any machine movements. So you will see that is this, and now after the milling is done, I think this down, yeah, the milling, and then comes the drilling, and then make this a bit slower. After the drilling, you will see that by just one step, the IPW is just moving to the sub spindle, and now the rest milling is cut with sub spindle. I stopped the simulation. And most CAM system, and this is also a common way in NX, using just the movements of the axis. So they just move this spindle to a certain position. Say to this position here, they pick a point, and the sub spindle is moving to this point, grab the part and move it back. So that's the standard. But as I say, we want to use some special controller or machine tool functionality, some special cycles. There is a cycle in the numeric controller which moves the sub spindle to the main spindle, and it moves the sub spindle until it hits the IPW, until one of this, the clamping is hitting the part here. And by you type in a certain pressure where the machine is moving, and until it hits the part, it stops moving, it grabs the part, and it moves back. And this, as I say, is a special machine tool cycle which I can simulate in NX. How I do this? That's also quite easily, because this functionality is already in NX Train in the standard environment. It's part of a mill control operation. You can also add it, by the way, in a generic motion. I show it in the mill control operation. And in mill control you have a lot of special machine function, like here the numeric stuff, and you have also here at the end this workpiece catch to sub spindle and this transfer to sub spindle, this FXS function. And as you can see, that's quite not so nice to select here the right machine cycles. There is also a way in NX to allow easily create your own templates based on these cycles. So you just create new template and you select some objects out of this cycle list. I have already done this as an example by these machine specific cycles. And if you do this, you get a new icon, and you can also add a picture like this. It's just a JPEG to explain functionality and what's going on with this cycle, and you define this, hit OK, and now you will see the parameter of the cycle. It's more or less the same as you select it from a list, but it's just a much more easier way to use this cycle. And now I position my sub-spindle, say, at this point. And remember, it's only an approximately point because I mentioned we are using this. I'm using this travel to fixed stop. So I just define this point. Need to regenerate this to operation. And this is how my IPW looks like. And the point I defined, if you remember, is here. If I go now and simulate this, you will see that the system is doing the following. It's starting the IPW a bit out that we can see some movements. A bit faster until the main spindle is done. So you will only see some steps, but after it comes to the right position, I slow down. So it's milling, and now comes the last operation, it's the drilling, and now you will see that the main spindle is coming, and it's not going to this point. It goes to a slow feed rate until it hits the part, and sometimes it hits the part, which is right now. And now if it is hit the part, it grabs the part and moves the part back to the sub-spindle. That you see that this is really trying to hit the part. If I do something wrong here in my programming, for example, I define a point which is too far away from this collision. The collision is somewhere here, and I put a point somewhere here. And if I now try to simulate the same, you will see that I get an error message. This error message is not an NX error message, it's an error message from the real machine tool. It's a controller error message. And the error message will, hopefully the point is far away, the error message will just give me an information warning that he did not find a collision between the sub-spindle and the part. So let's see, that's the two operation, and now comes the last drilling operation. And now the sub-spindle will move and come, and now it goes to a feed rate, and now it checks for collisions at this point, but you will see that it's too far away, and it will not find a collision within this 100 millimeter range, which I type in the dialog. And after a certain, it will give me a controller error message here in the dialog. So you see, comes here with an error message, a travel to fixed stop not reached. So it travels this 100 millimeter, which I type in. You will see it here in the ANSI code as well. And because it hit not the IPW, it gives a controller error message to NX, and NX stops the simulation. So you see with this example, you see how related, how close we are on the machine tool. We are really using the same cycles as the machine tool, and we are really doing the same thing as the controller and the machine tool is doing. So, and with this, my examples are finished.
Uwe, can you show us how you configured the system to do that automatic transfer of the IPW from the main to the sub-spindle? I think it would help to see that.
So I think he's then talking about this functionality. So if you are here in the geometry view, it's important that you have this structure, which you can see here. Not this one, not this one, this structure, and not this one. You have to have a master blank, that's this blank, and you have to have your main and sub spindle and you have to have two workpieces, one main and one sub-spindle. These two workpieces do not have a blank assigned, as you can see. There is this master blank assigned, which is okay for this and for this. And because of this master blank inside this operation, so I have to go with the mouse here, there is this specify blank geometry and there's this button. If you don't have this automatically positioning, you can select the reference point and the target point to say from here to here. But this automatic position uses the assembly structure, and the assembly structure is coming out of these two workpieces here with these two MCSs behind. It's important to have this structure here. If you don't have this structure, if you have more than one workpiece, or if you have parallel workpieces here, if you have parallel main spindle coordinate system here, you will get a problem with this automatically position. So you have to have this structure, and as I say, I'm not 100% sure if this functionality was in NX 7.5 as well. I think so, but let's see. Oh, I need to have the turning workpiece. You see, automatic was here as well. Yes, in 7.5. But it's grayed out. It's grayed out if you don't have the right structure. If it is grayed out, you don't have the right structure. Then you have to refer to this correct geometry view structure. If the structure is not correct, the bottom is grayed out. If you go to your installation environment where you have installed NX, I go to 8.5. If you go to the Mach folder, if you go to the samples, there are NC simulation samples, and there is one NC simulation sample, it's called Sim15. You can open this and have a look for the structure. This is the out of the box structure.